Okay. So this is problem 7.4 in your book. It tells you that the beam weighs 280 pounds per foot, and it wants the normal force, the shear force, and the bending moment at C. So how do I find, if I cut it here at C, what side of the beam do you want to work? Do you want to work the right hand, I guess the upper part, or the lower part? I guess I would probably be more inclined to work the upper part because I know at B I only have one unknown. Right? If I cheat a little bit and use the diagram as my free body diagram, you can see that I've got a y component and an x component at A, and then I just have a force at B. Also, the beam weighs 280 pounds per foot, so that means that I have to multiply it by the length of the beam, right, to get my total load. And where would it act, that force act? In the center, right? So that means that right here in the center, I have a force of 280 times 10 feet, so that'll be 2,800 pounds acting right in the center, which I guess if I marked it this way would be 5 feet. So if I'm going to cut it here at C and work the upper piece, I want to find B. So to find B, what do I need to do? Some moments a day. So what's some moments a day? I'm using right-hand rule for my sign convention. So if I sum moments at A, what do I get? Well, I have my 2,800 pound force creating negative moment. And it has a moment arm of not 5 feet. What's the, it's a 3, 4, 5 triangle, isn't it? 3, 4. So it would be 3 feet. And then I have my reaction at B, which is creating positive moment. And it has a moment arm of 8 feet. So what's my force at B? Let's see, that's 2,800. I got 1,050. Did you guys get that? Mm-hmm. Okay, now I'm going to cut this structure. So there's my cut at C. I've got my force acting at B of 1,050 pounds. And then internally, I'm going to assume I have a normal force, a shear force, and a bending moment. And I'll put subscript C's on each of them, and I'll also put a little plus to indicate that I'm using the positive sign convention, just to make sure to see that. The length of this thing is, what is it, 7 feet? Right? What else am I missing? Well, the beam still weighs something, right? That chunk of the beam still has some weight. What is the weight? 280 pounds per foot times 7 feet. I got 1960. So that means I have an additional force of 1960 pounds. And that particular location is half the distance, or 3.5 feet. Okay? So you can see I've got some work to do because with the normal and the shear force, I'm going to have to break all these things down into their components. For the moment, that one should be pretty easy to do. So let's tackle the moment first. So let's sum moments at C. Make sure the whole structure is in equilibrium. So what do I have? Now remember, I'm using a right-hand rule for my moment, so this is actually a negative moment for statics. The weight is going to create also negative moment, so that's the 1960, and that's pounds. And what's the moment arm for that? What's the distance between C and the 7? That's kind of tricky. Don't forget that the slope here is 3 to 4, right? So I should have the horizontal distance should be 3/5 of 7, right? Is that right?
The distance from C to the center of the beam?
Not the center of the beam, the center of this section. It's only 7 feet long. So it's 3.5 feet up this way, but what's this distance?
4.2.
Sorry?
3/5 of 7.
4.2.
Yeah, so 3.5, and you got, what'd you get?
You said it would be 3/5 of 7?
No, of half,
Oh.
because it's in the center. I said 7, but you're right, it should be 3.5. I got 2.1. You guys get that?
That's right.
Makes sense.
So I want 3/5, but remember this distance is half the distance. So it should be 3/5 of 3.5. I got 2.1. And then this creates positive moment at the top, my 1050. And what's this moment arm? It's this distance. That'll be 4/5 of 7. I got 5.6. That makes sense? We should be able to solve for the moment at C, whatever that is. I got 1,764. Did you guys get that?
Yeah.
Yeah? And I got it to be positive. Does that make sense?
Mm-hmm.
1,764, and that'll be Does that make sense? Seems like it does to me. Now the fun comes. This is, we haven't had fun yet. Now the fun starts. So how do I find the normal force and the shear force? There's a couple ways to do this. All my forces are in kind of different coordinates. So there's two ways. If I use standard XY coordinate system, you see my two forces are either X or either Y, but you'll notice my shear force has both an X and Y component, and my normal force has both an X and Y component. You don't want to write two equations and two unknowns. So what I'm going to suggest that we do is assume a different coordinate system, one that's inline and then perpendicular. So my unknowns, the normal force and the shear force, now are either all x or all y, and I can break these down into their x and y components. Everybody see that? I think it'll, so I'll call that x prime and y prime. So now if I sum forces, say in the x prime direction equal to 0, you'll notice that the only thing in the x prime direction is just my normal force. I don't have to worry about breaking it down, but I do have to break these guys down. So what's going to be the normal component here, this piece? What's going to be 4/5 of that, and it's going to act negative. So I'll have 4/5 of 1960. And then you can see up here at the top, my reaction force. I've got a component like this, component like that. I probably should have drawn these in. Maybe you can help you see them a little better. My free body diagram is getting a little crowded. So my component here will be 3/5, and it's also negative. So 3/5 of 1050. So it looks like my normal force is going to be negative, and whatever all that is. I got 2,198. That sound reasonable? For a problem that's early in the book, this was a little challenging right out of the gate. I did this wrong. This should have been my positive x, not up. So now we'll do positive up for summing forces in the y prime direction. We'll do the same thing. So now I've got my shear force positive. The 1960 has a negative component, and that's 3/5 of 1,960 pounds. And then up here, I have a positive y component, and that'll be 4/5 of 1,050. So it looks like the shear at C, I think it's going to be positive. Let's see, 1,050. 1960. I got 336. You guys get that? Looks like it's positive. So what was the thing to see here? When you go at an angle like that, remember these forces are always normal and perpendicular. So that just creates some challenges for you with the geometry. When your elements are horizontal or vertical, it makes it a lot simpler. Any questions about this one before we stop? Okay.